All right, so this is the lecture for 5.1. We've talked in chapter 4, we talked about the introductory models of the atom, and 5.1 is the development of that atom to further advancements and to our current model of the atom. And so we're going to go through all of the models so far and the scientists who have helped in these discoveries, but we're also going to fill in some class notes. So in section 5.1, go ahead and flip to the page that has the quantum mechanical model as one of your bold terms there, and we're going to find our first asterisk. And that asterisk says electrons in this model don't have exact paths. Instead, they have, and we're going to fill that in, okay? So instead, they have probabilities of existing inside an area around the nucleus. Probabilities of existing inside an area around the nucleus. Probabilities of existing inside an area around the nucleus. We're going to keep going just a little bit. A cloud without a definitive boundary. A cloud without a definitive boundary. So in our current model, and we're going to talk about this more in a little bit, our electrons do not have a boundary on their atom. There's not a point where there's never going to be an electron past that area, okay? So the probability decreases as you get farther and farther from the nucleus that you're going to find an electron out there, but it's never a boundary. It fades out and it doesn't ever become zero, truly, okay? All right, atomic orbital. The definition from the book says an area of high probability of finding an electron with a specific amount of energy, okay? So think of those as areas of high probability of finding electrons, okay? It's a space around the nucleus. It can have a different shape depending on the orbital, but it's where you're going to have a high likelihood of finding an electron, okay? And those electrons have specific energies, and we're going to talk about that, but that part of the definition isn't as important to us as the fact that it's an area of high probability of finding an electron. If you're very likely to find an electron there, somewhere in this area, that's an orbital, okay? All right, and underneath that, we have two asterisks. We have energy levels and we have energy sublevels in the quantum mechanical model. Okay, energy levels are going to be layers of electrons in an atom. That's one way we can think of them, okay? Layers of electrons in an atom. Layers of electrons in an atom. And those layers are represented in the periodic table, okay? Each row in the periodic table represents one layer of electrons. Each row in the periodic table, represents a layer of electrons. Each row in the periodic table represents a layer of electrons. So if we're looking at the periodic table, it looks like there are 9 layers here, okay? But there are only 7 rows in the periodic table, and those represent our layers, okay? These 2 that are down here, they actually fit in where this bolded line is here, okay? They squeeze in here, and that makes the periodic table really long, stretched out, okay? But it does not give it 2 additional rows, okay? So there are only 7 rows in the periodic table. We have 7 layers of electrons in our largest atoms. Okay, the energy sublevels. Energy sublevels. Okay, sublevels is smaller than a level, subatomic smaller than an atom. So sub means smaller, right? So in each level, we have sublevels, smaller than a level. And those are the orbitals, Okay, so sublevels are also called orbitals, which again we defined above as an area of high probability of finding an electron. Okay, so orbitals, another way to look at an orbital is part of a layer. Okay, sublevels are part of the levels, orbitals are part of the layers with a specific shape. Part of a layer with a specific shape. Okay, keep going. Defined by mathematical equations. Defined by mathematical equations, those are the Schrodinger equations. And this is math that's way above this course. We're not going to go into that math, okay? But it is areas in which electrons move randomly. So part of a layer with a specific shape, defined by mathematical equations, in which electrons move randomly. In which electrons move randomly. Okay, so we just covered pieces of the quantum mechanical model, and we are going to cover those again. I'm going to erase this now, and we're going to start talking about the early atomic models before we go into the quantum mechanical model, our current model. So pause it if you need it, but once you've finished copying this into those asterisk areas of your notes, in the class notes early atomic models section at the bottom of the page, we're going to need a table with these headings. Okay, and so if we can't read those, I'll read them to you real quick. Scientist, discovery, model, description, and limitations. Okay, we're going to do all of the first 4 models of the atom in this space. So we're going to need places for 4 models. So pause the video if you need to, write those headings out, and then we're going to fill in underneath and make a table for our early models. Okay, so our earliest scientists, so somebody who actually did experiments, not just philosophized about the existence of an atom, would be Dalton. Okay? Dalton. And his theory was produced in 1803. And we credit him with the discovery of the atom, because he's the first person to come up with evidence to support the existence of the atom. So his discovery is just the atom. Now remember, when he was doing this, he thought atoms were indivisible, not invisible, indivisible, okay? He thought you couldn't get any smaller than an atom. And so his model is just that. It's just a little sphere that can't be divided, okay? So description of that model, small hard sphere, small hard sphere, no subatomic particles. Small hard sphere with no subatomics, okay? And the limitations are that it had no subatomic particles. That's a pretty big limitation now that we know that there are particles smaller than an atom. So who came along and discovered there were particles smaller than an atom? Okay, well in chapter 4, we've already learned about this scientist. His name is J.J. Thomson, no P, J.J. Thomson. Okay, and this was in 1897. He ran electricity through a tube, a vacuum tube that had just a little bit of gas in it, and a light appeared. And when he brought a magnet near that light, the light beam would bend towards that magnet or away from that magnet, depending on which side of the magnet he brought near the beam. Okay, so this was a cathode ray tube experiment that was described in chapter 4. And he discovered that the beam was made out of negatively charged particles because of the reaction to the magnet. So those negatively charged particles and the electricity he used to create that beam, he called them electrons. Okay? So he's discovered the electron. All right, so now the model of the atom can't look like this anymore. This is what everyone thought it looked like, but he knew there was something smaller than the atom, and it had a negative charge. And so he had to create a model that had this negative charged thing in it. And if there was a negative charge in it, there had to also be positive because the atom is neutral. So they had to balance out there. Okay, so he created a model that looks like this. It's a positive ball of matter, and it has negative electrons stuck to it. Okay, so this part is positive. And then it had negative electrons. I'm just drawing circles with a little negative sign in the middle, stuck to it. Okay. Negative electrons stuck to it. And this is called the plum pudding model because the popular dessert in that time was kind of like a bread pudding. It was a kind of a cake, and the plums were dropped right on the top of it. And so that's what this reminded him of. Okay. So this is our plum pudding model. Negative electrons, negative electrons, see if I can spell today, stuck to a positive ball of matter. Negative electrons stuck to a positive ball of matter. So limitations to this model. Well, the electrons aren't moving. And there's no nucleus. So in his model, the mass of the atom is spread out throughout the sphere. Okay? And so that opened up the opportunity for someone to come along and discover that the mass of the atom can't possibly be spread out this much. And that was Ernest Rutherford. Okay, Rutherford. Now Rutherford came and did his experiment and created his findings and conclusions in 1911. He was actually a student of Thomson's. And he's credited with discovering the nucleus. And the empty space that surrounds that nucleus. That he discovered that most of the atom was empty space for volume-wise. Okay? All right, now his model. We're going to go ahead and put the nucleus. I'm just going to do two filled in circles and two open circles to kind of represent our nuclear particles there, protons and neutrons. And this is kind of the classic Jimmy Neutron model. Okay, so the cartoon atom that we see everywhere, even in the kind of national scientific institutions, they have this looking, this atom structure on their logos and stuff because it's cool looking. Well, it's very outdated. We don't use this model. We're 2 models past this one, but we'll put those electrons out here kind of zooming around a nucleus, okay? All right, so description. It was a small, heavy, positive nucleus, small, heavy, positive nucleus, mostly empty space. Okay. Small, heavy, positive nucleus. You could write that the electrons are orbiting around that nucleus. Mostly empty space between the two. And the limitations. Oh, wait, first off, the name of this model is the nuclear model. That was the focus of his model, was that nucleus. Okay. But the limitations, the electrons are in orbit. Okay, I really wish they had used a different word than orbital for our current model because it's too similar to orbit. But orbit is wrong, okay? That is not how electrons move. So electrons are in orbit, and it lacks different energies for electrons. It lacks different energies for electrons. So all the electrons in his model are the same distance from the nucleus as each other. Okay, so then Rutherford's student, well, maybe not, maybe classmate, we'll see. I can't remember. But Bohr came along, and he did his experiments in 1913, so just a couple of years after Rutherford. Okay, that doesn't mean he wasn't a student, but I can't remember. I'd have to look it up. All right, Bohr, 1913. He's credited with discovering that there are different energy levels for electrons. Okay, so energy levels for electrons. Okay, and this is part of our 5.1 reading for today. Bohr came up with different energies. He noticed that different things have different colors of light emitted from them as they change energy. It's really something you can see in slow motion when you heat up iron. You can see it goes from red to orange to yellow to white hot, and that's different amounts of energy being given off by the atoms of the iron. Okay, so he did experiments with hydrogen. Hydrogen was what he used in his experiments, and he created a model where he still has the same nucleus, okay, because that piece still hasn't changed, okay, and he used math to kind of show that electrons could be at different distances from the nucleus. Now, after you draw your first couple of rings, the rings start to get closer to each other because their energy differences decrease. And so there was a good picture of a ladder in your textbook where the rungs of the ladder got closer to each other as you went up the ladder. And that's kind of how Bohr modeled his rings. They get closer together as you get farther away, because as the electrons gain more energy, get farther from the nucleus, the difference in energy between them and the previous electrons is smaller, okay? And that piece, that energy change, is still accepted today. We're going to talk about that some more, okay? But let's describe this. This is circular orbits. Circular orbits of specific energy where electrons travel. Okay. Orbits get closer together. Orbits get closer together as they get farther from the nucleus. Orbits get closer together as they get farther from the nucleus. Okay. He discovered quantum leaps. Okay. Quantum is a specific quantity, a specific amount. Leaps are jumps. Okay, now electrons don't have legs, but they jump different energy amounts, and then they fall back and they give off light. We're going to do some labs with that, okay? So quantum leaps with energy changes. Quantum leaps with energy changes. And we can call this the Bohr model, or we can call it the shell model, because these are kind of like shells. So I ran out of space, but we can call this the Bohr model or the shell model if you wanted to refer to it in words, okay? So either one, Bohr model or shell model. And the limitation for his model, it described hydrogen perfectly, okay? But it doesn't describe anything with more than one electron because of the orbit, okay? That's the only thing he's missing. So electrons orbit, that is the limitation. That is the piece that is wrong with his model. But the energy levels, he did a great job with, okay? So now we're going to turn to that next page in your notes packet. Well, you don't have to turn the page, but at the top of the next page, we're going to do this same chart for our current model of the atom, which is the quantum mechanical model. And we're going to talk about orbitals in even more detail. So I'm going to erase this, make the same headings at the top of the next page, and we will continue with our current model. Okay, so our scientists for this model is Schrödinger, Heisenberg, and others. We're going to give all of them credit, okay? Schrödinger applied the math to figure out orbitals. Heisenberg had the uncertainty principle, and others have contributed as well. And the year is 1926 when this model sort of got solidified, okay? So the discovery, the major discovery is orbitals. Whoops, forgot a letter. Those letters at the end are super important. AL makes an entirely different word than orbit in terms of meaning, okay? Okay, now drawing this model is not easy. If you have a pencil, it's a lot easier than if you don't, okay? So the nucleus, I'm gonna go ahead and draw the nucleus the same way I have been drawing it. And then probability of finding electron orbitals, right, is higher at the center and gets lower as you move out from the center. So ways that you could do this, you could do dots and have, you know, intense amounts of dots towards the center, and then as you get farther out, have fewer and fewer dots, okay? You can use shading. If you have a pencil, you can shade it darker around the nucleus and then get lighter and lighter and lighter as you go out. I'm going to sort of just draw a cloud. I'm going to try to do some sort of shading as I get closer to the nucleus. And again, I'm trying to make this look spherical, but with a whiteboard marker, not the ideal drawing tool, okay? So we're trying to go for a spherical look. These lines are not paths that the electrons follow. This is just my shading with a whiteboard marker, okay? So it gets farther and farther out, less likely to find an electron, okay? And ideally, it would fade into nothing so gradually you wouldn't even be able to tell. Also, this is not to scale. The nucleus is 1/10,000th the diameter of the atom. So it would be impossible to see the nucleus if my atom was this size. It would be too small, okay? If my atom was just a tiny little dot in the center of this whiteboard, the entire atom would be the size of the whiteboard, maybe even a little bit bigger as far as the diameter across the atom, okay? So 1/10,000th, okay? Okay, but again, every time you draw a model, the drawing is going to have limitations, but the model description is where we're going to cover this, okay? Electrons move randomly. Electrons move randomly in orbitals of specific energies. Electrons move randomly in orbitals of specific energies. No orbits. Okay, an orbit is a fixed path. Our planet orbits the sun and it's on a path, and we can predict where it's going to be next. Orbitals are spaces that are three-dimensional. They have specific shapes, specific energy, and they have high probability of finding an electron. But you won't always find an electron there, and you cannot predict where the electron's going next, okay? The nucleus has protons and neutrons. Nucleus has protons and neutrons, and is much smaller than the atom, okay? Limitations, none. This is our current model. Right now, we have no limitations for this model, okay? I'm sure that with future research, we'll be able to describe it even better than what we could in 1926. We probably already can with particle physics, but the overall model has been this since 1926 and doesn't have limitations as far as it describes the atom. Now we're going to talk about orbitals. So in that same space, give yourself a little section for orbitals. I like to forget the R. Orbitals make up the electron cloud. So that's my cloud up there, and it's made of orbitals. Okay, orbitals make up the electron cloud. There are 4 types of orbitals, and they are given a letter to represent them in the Schrodinger equations. Now, we came up with words that match those letters to sort of describe their shapes. Okay, s orbitals. S orbitals, they are spherical. Okay, they're spheres. They start in energy level 1. They start in energy level 1. And there is 1 per energy level. So, in other words, we talked about the rows of the periodic table representing the layers of the atom, or the number of levels of energy. There's an s orbital in level 1. And there's 1 in every energy level after that. So each energy level has 1 s orbital. Okay? Remember, that first energy level is the first layer. That's the one that's closest to the nucleus. And then we get farther for layer 2, farther for layer 3, but it's closer together, farther for layer 4, et cetera, et cetera. And each energy level has 1 spherical shaped orbital where you're going to be likely to find electrons. Okay? All right. Next type is p. Okay, p orbitals. A p orbital looks like if you took 2 balloons, inflated them, and then tied them together at the knot, kind of have this shape here, okay, like this. So this is, it's kind of a peanut shaped, but really, really tiny at the center, okay? So we call this peanut. Not a perfect word, but it does start with P, and it kind of gives you an idea of that shape, okay? Now these ones start in energy level 2, okay? Energy level 1 is so small, all it has is an s orbital. Peanut orbitals, or p orbitals, start in energy level 2. And there are 3 of them in every energy level, level 2 and above. So 3 per energy level. And they lie on the axes, and you can see a picture of this in your textbook, but you have px, py, and pz, and we label them that way. If you go into AP Chem or College Chem, you will get into those specifics. Okay, next we have d orbitals. D. Now a d orbital kind of looks like if you took 2 p orbitals and you cross them at the center, so you have 4 lobes to a d orbital, and we call it a double dumbbell. You dumbbell and dumbbell, and you cross them at the center, you have 4 sections, okay? So that's our d analogy for the shape. Double dumbbell. I bet you can probably guess where they start if you follow the pattern here, but they start in energy level 3. And again, we're following this pattern. There are 5 per energy level. 5 per energy level. So we're getting really complicated here. I'm going to draw a picture of kind of how these go together to make a cloud after we get through the last type here. Okay? All right, f orbitals. All right, f orbitals, their shapes are so bizarre that we just call them funky. Right? And you guys, we don't need you to memorize these silly words, but we do need you to know that their shapes are different. Their energies are different. The number that exists on each level are different, okay? We don't need you to know what shapes they are, but we need you to know that their shapes are different. They start on energy level 4, and there are 7 per energy level. Okay. Now I'm going to draw a picture of an atom using these orbitals to sort of represent where those electrons are going to be. Okay. You do not have to do this in your notes, but I just want to show you this is our picture, but this is where the electrons exist. Okay, in orbitals that exist in different energy levels, which are layers. Okay, so if this is my nucleus, this just dot that you probably can't even see in the video, okay, I'm going to go ahead and say energy level 1 is an s orbital. So here's my energy level 1, okay, s orbital. I'll make my nucleus big enough to see in the video, okay. Now, that's all that's in energy level 1. So now I'm going to go to energy level 2. Well, there's one s orbital in every energy level, so here's my s orbital, my sphere, for energy level 2. Okay, but a p orbital now exists as well, and not just 1, but 3 p orbitals are going to be added to level 2. They're going to reach within the same layer, so I'm going to go ahead and draw one peanut. Okay, that's 1p, that's my py, px. Now pz is lying on the axis that points out towards you, so I'm just going to go ahead and draw it kind of how we would do it in a math class. Okay, so there's my 3 p's. Now I'm going to go ahead and go energy level 3, and that's my s, my sphere. Here's my p, p, p. But now I have 5 Ds as well. So the d orbitals come in energy level 3. And a d orbital, I'm just going to draw 1. That's 1 d orbital, and there's 5 of them, okay? One of them is even spinning on its axis. So the d orbitals increase the complexity quite a bit. The f orbitals are crazy. Go ahead and look them up. They're really funky, okay? But can you sort of start to see, as we draw this layered thing, that the orbitals are overlapping a lot more in the center than they are out here, okay? It's a lot crazier in the center than it is out here. And so we're getting this cloud where it's more shaded in the center than it is farther out, and that's a higher probability of finding an electron closer to the nucleus than it is as you get farther away, okay? So we will never ask you to draw a picture that looks like this, but you can do a shading or a dot or some kind of picture with a cloud, and as long as you can describe what's happening here, we know you have the basic understanding of what our current model of the atom looks like. Okay, I think that is it. That is it for chapter 5, section 1. I believe the next assignment might be to finish the lesson check, but go ahead and check in Canvas and see what you're supposed to do next. So thanks for watching, and we'll see you in class.